Hello, everyone, and welcome to today's webinar on Planet 7, Realize the Potential of 5G NR with Accurate RF Planning. My name is Erica Collins, and I'll be your moderator for today. Before I introduce our speaker, Gregory Donard, I'd like to go over a few housekeeping items so you know how to participate in today's event. If you have joined the presentation using your computer speakers, but prefer to join over the telephone, just select telephone in the audio pane and the dial-in information will be displayed. To submit questions at any time during the presentation, please type them in the questions pane of the control panel. Questions will be collected and addressed at the end of today's presentation by our presenter, Greg, and by David Nathan, VP of Radio Engineering Solutions, and Reggie Labour, R&D Director. And now, I'd like to introduce our speaker, Gregory Donard, Product Manager for Infovista's Network Planning Suite of tools, which includes Planet, Ellipse, Planet Engine, and Planet Server. Greg has a master's degree in electronics and telecommunication systems and has 14 years of experience in the wireless telecom industry, working for Marconi, Ericsson, Mentum, and now Infovista. He has extensive expertise in network planning and optimization for most radio access technologies, including 5G NR, LTE, Wi-Fi, and others. Welcome, Greg. The floor is yours.
Thank you, Erica, for the introduction. Let's go through today's agenda for the presentation. So we'll start with a brief introduction, and then we'll go into the 5G details. So 5G, when can we expect it to start with? There's a lot of hype on 5G these days. We'll go through the key technologies that are underpinning the 5G NR, and then we will discuss some key use cases and early feedback that we've had through early trials or even early deployments of 5G technologies. So those use cases will be the 5G NR technology, fixed wireless access, and massive MIMO as well. As Erica mentioned, we will finish with a conclusion and a Q&A session, so please feel free to ask any questions you may have through the chat box in the GoToWebinar session. A few words on Infovista to start with. We're a global company. We have more than 1,500 customers in more than 150 countries. We have Infovista acquired a few companies in the recent years, starting with Mentum in 2012, Ixio in 2013, Ipanema in 2015, and then Thames in 2016. Through those acquisitions, we've acquired a lot of engineering expertise. On the Mentum side, as an example, we acquired the network planning expertise. As Erica mentioned, this is where I come from as well. And Ixio, we acquired optimization expertise with Thames network testing, as an example. Our revenue for 2017 was approximately $180 million USD. We have various product offerings to offer through the whole network cycle. So products to plan the networks, deploy, operate, optimize, and monetize. Today we will be focusing on network planning, and this is the green part over here on this diagram. A few words on market trends. So you may have seen this report from last November from Ericsson on the Ericsson Mobility Report, November 2017. Year on year, we can see a 50 to 60% increase in terms of traffic. So it's a big challenge for the operators to cope with that traffic demand and the traffic increase. And there is always some research to make sure that this traffic can be served by the technologies. So to cope with that traffic demand increase, the operators are looking at multiple solutions. Introducing 5G technologies is one thing, 5G radio standards. There is also a need to densify the networks and to roll out new technologies such as 3D beamforming or multi-use MIMO. It's interesting to see as well that the expectation is that by 2023 there will be already like 1 billion 5G subscribers, or this is what is expected. It looks like a small part on the graph here, but it's still quite a significant number. It's predicted to be the fastest takeoff of all wireless generations. Here are the key features and use cases that are relevant for 5G. The legend over here is that the green dots mean that the use cases, the features are very relevant for those use cases, and the orange dots mean that there is applicability for that. On the horizontal axis over here, you can see the features, so millimeter wave frequency bands, so using like frequency bands like 15 gigahertz, 28, 39, 60, you name it. Massive MIMO, which we will discuss extensively throughout this presentation. And then you have 5G NR specific features, and more specifically, flexible numerology and flexible structure. And the concept of network slicing that is quite trendy these days as well. And on the left side here, you can see the use cases. So fixed wireless access, enhanced mobile broadband, ultra reliable low latency communication, so critical communication here, and then massive IoT. Okay. Here are the use cases that we will discuss in more detail in this presentation. So the first one will be 5G NR network planning and network dimensioning. The second one will be fixed wireless access dimensioning. And the last one will be about massive MIMO coverage and capacity planning. Before we go into the details of those use cases, we would like to have a quick poll, and that I will let Erica present this poll to you. Thank you.
Okay. Thank you, Greg. So the poll question for today is, when do you expect to start 5G network planning activities? So the choices are in 3 months or less, in the second half of 2018, in 2019, in 2020 or later, or not involved in network planning. So we're going to give everyone about 30 seconds to make your selection, and then we will display and comment on the results.
Thank you, Erica.
Okay, so the poll is now closed. So, you know, I'm not really sure about you, Greg, but to me, the results here are very interesting, even though they're not very surprising, especially after seeing firsthand at Mobile Congress this year how 5G is really starting to become a reality. Do you agree?
Yes, that makes a lot of sense, what we're seeing here. There's a lot of hype on 5G, and we've seen a lot of demand already for network planning for 5G technologies, whether it's for fixed wireless access purposes or 5G upcoming deployments. This is very much in line with what we've seen in the last 3 to 6 months for sure. Okay, thanks everyone for participating to this poll. That's very interesting. We'll now go through the 3 use cases that I just quickly presented, and we'll start with 5G NR network planning and dimensioning. So we'll start with a few key concepts and feedback that we've gathered, or that we gathered from 5G NR trials. First of all, on the top line over here, you can see some of the challenges that are offered with 5G NR. The first thing to note is that you have 3 use cases to be handled with 5G NR. URLLC, so ultra reliable and low latency communications, massive IoT, and enhanced mobile broadband. It is quite clear that the #1 priority will still remain mobile broadband, as it was for previous radio access technologies, but now the 5G technology has to handle more use cases. So again, like critical communication, and then massive IoT there. So that challenge can be treated through the help of the 5G NR technology, and this brings us with a relatively complex frame configuration that you can see here, and we'll talk about this in more detail in a few minutes. The next thing to note is that higher frequency bands are being looked at. So we're looking at the CBRS bands, so 3.5 gigahertz, and millimeter wave bands. We'll talk extensively about millimeter waves in a few minutes. But this also leads to the fact that the cell range decreases quite significantly, which means that to have the same amount of coverage that you would get with smaller frequency bands, then you will need to densify the network, basically. And on the right side here, this is a picture from the 3GPP standards. As you probably know, the 3GPP standard came up with release 15 at the end of last year, so end of 2017. And there was a non-standalone version of NR that was designed or released. And in release 16, in June this year, the standalone version of NR should be released in there. So non-standalone means that you need to rely on the LTE core network to have NR coverage for your subscribers. At the bottom here, you can see the some of the features that can help to cope with the challenges I mentioned above. So as I said, so complex frame configuration there for NR. Then you can see 3D beamforming here, which is a key concept which can help increasing the coverage, especially for users that are pretty high up inside the buildings there. And then network densification, where you will need to put more and more cells in the network. And then on the right side here, you can see a mix of LTE and NR cells that have to work together. So when you do your planning, you need to consider both technologies together, pretty much. In terms of site density, what we've seen so far in the trials that we've been involved, like for dense urban areas at 28 gigahertz, we've noticed like 250 to 300 cells, so about 100 G node Bs per square kilometer. That's pretty much what we've seen for the early deployments or early trials, I should say. Let's move on to the frame structure. So as I said, it's a little bit complex as a frame structure, but this is to make sure that the three use cases that were presented above can be covered. So first of all, you may note that the frame duration is 10 milliseconds, which is the same length as what we had or what we have for LTE, and this is done so that you can have coexistence between LTE and NR. Okay? Then you will see a concept of flexible numerology. In OFDM, so for LTE, the resource elements had a 15 kilohertz bandwidth. This was a constant. Now, to handle more use cases and more frequency bands, it was decided to introduce the ability to have different subcarrier spacings. So you may have like 15 kilohertz, 30 kilohertz, 60 kilohertz, 120, depending on the frequency band and depending on the use case that you're trying to achieve, then you may use a different numerology. For mobile broadband, as an example, you may want to use a higher subcarrier spacings or larger bandwidth for subcarrier spacings. Massive IoT and URLLC communications might be different. Along with that, you have a concept of scalable TTIs, so time transmission intervals, and this is also done so that you have flexibility for the use cases. For so low latency communications, you may have like a need for slow TTIs or non-slot based scheduling as well. Okay, when it comes to 5G network planning and dimensioning, there are three things to consider to start with. So it's the fact that you need to define the spectrum that you want to use, the GNOB configuration and the UE configurations. Then you can run your network simulations, network analysis or Monte Carlo simulations, and then run network optimization, or so for dimensioning first, so dimensioning the network, so about assessing how many GNOBs you will need to cover a particular area, and the optimization of the cell or the antennas. So we'll go through that directly through Planet now. So this is Planet 7 that we released Mobile World Congress earlier this year. And the first thing I would like to show is the typical start of a project here, where you would go into your network settings, and this is where you define the technologies that are being used in a particular project. So in this case, it's CDMA video and LTE and NR. And you would want to go in the spectrum allocation where you would add the spectrum that you're interested in. So in this case, it's a TDD, a duplexing mode, TDD frame, 3.6 gigahertz. But if you click on the add button here, you can choose the standalone or non-standalone NR mode in the first place, the duplexing mode if you want to use FDD or TDD TDD frame configurations, and then the carrier bandwidth. Okay, so carrier bandwidth in NR, so far in release 15, you can go up to 100 megahertz. In some of the trials that we went through, carrier aggregation was used as well, so you can have 4, 8 carriers, each of them being with a 100 megahertz carrier bandwidth, sorry, which of course then allows you to offer like massive data rates. If you use like 8 carriers of 100 megahertz each, then that really gives you like a nice throughput there. Okay, in the NR configuration as well, one thing that is interesting is the ability to define the numerologies that you want to use. So it is possible to use different numerologies for synchronization signal and the BCH channels on the one hand, and then the subcarrier spacing or numerology for the PDSCH, so for the data on the other hand. You will see the choices here are based on the 3GPP standards. So depending on the frequency band that you're using, and depending on the channel that we're looking at, then the choices will be different. Okay. Once you're done with that, so then you have the ability to define your GNODBs. So if I go into the site editor here, so multi-technology site, as you can see here, you have the ability to define your NR GNODBs on the left side here. You can add base stations, okay, so NR base stations or NR GNODBs in there. Once you're done with that, you can go through network analysis, and we have a concept of network analysis templates so that you can create, define your settings once and for all, then we use those settings to create network analysis for different groups of sites or different simulation areas, basically. One thing to note here is the selection of layers that you want to that you can pick and choose from. So best server related layers, reference, synchronization, and broadcast, and then data layers. So for the PDSCH and PVCH, so the downlink and the uplink. Some interesting layers like the CSI RSRP, SSR SRP. Those are key layers for coverage, and then PDSCH SANR, PDSCH data rates are key as well for NR planning. A quick demo on the on a network analysis that you can generate. So I just create a copy of this analysis, and then you can pick, you can modify the SSR SRP threshold. So I can put neg 125 dBm as an example here, and then it should start my my network analysis. I think we have about 125, okay, 119 cells being considered for this analysis in Atlanta, if I'm not mistaken. Yes. Okay. So while this is being generated, this is a modeless dialog, so you can do other things at the same time. You can minimize the dialog if you want, or bring it back up this is up to you. I can show you a couple of layers that are generated. So one layer, of course, that's of interest to everyone is the best server layer. So for each location, it will give you which cell is serving the particular location. Then we can go into SSRSRP levels. So if I click on model height, then that gives you the SSRP levels in there. This analysis was generated in 3D, so we have layers at different height above the ground, different height above the ground level. And you can see again more layers here that were generated in 3D. This analysis should be about done here. So give it a couple more seconds. Okay, this is done now. Okay, and then I think this is what I named it. So again, if you want to look at the RSRP levels, this is what you get. So RSRQ, SSRSRQ levels as well here. Now on the network dimensioning side, so this is handled with the automatic cell planning tool that we have in Planet. I created an optimization here, or optimization scenario, so really a dimensioning scenario in this case, and I will launch it here. So this is about selecting the cells, or deciding which cells you should be putting, or you should be selecting or deploying first for your 5G NR network. It is worth noting here that we're looking at 3.6 gigahertz for this presentation, and you can see the ACP is selecting sites here to maximize the SSRSRP coverage. So it ranked about 40 sites here, and depending on your criteria, so your optimization criteria, you will select, you can decide the number of steps or number of sites that you want to select. So you can look at the report for this. I will minimize this while the ICP is generating the layers. So you can look at the report for that in terms of goals here. So it should pop up in this dialog, and then you can see on the left side the number of steps, which corresponds to the number of sites that get added, and then the SSRSRP quality, which gives us the percentage of traffic that is served after each step has been added. If I click on show graph here, then you have a graphical representation of the data, which is quite nice to select again to see where the curve is flat, which means that if you're adding sites on top of those, then you're not really getting that much coverage. Now, if you have your design guidelines, so maybe you need to serve, let's say, 90% of traffic, then you will look at this particular step. So you will know, okay, I need 21 sites here, 21 G-node Bs to serve this particular area. Okay, so I will now go through the second use case that we have for this morning, which is about fixed wireless access. So fixed wireless access, this is about replacing the last mile, even though it's not really a mile, it's way smaller than this, but this is about replacing wire lines that are used today to deliver cable communication, and to replace those with wireless links. Okay, so put radio sites and provide high video content to households in suburban areas mainly, but also in urban areas. For this, millimeter wave bands have been of prime interest because in millimeter wave bands there's a lot of spectrum that can be used, and that can deliver high throughput. 3D beamforming is a key concept for fixed wireless access, as you can see on this picture over here. On the screenshot on the right side here, it allows to direct the beams towards the households, and we'll go through that in a few minutes. The CPEs typically can be mounted on rooftops, or they can be also inside the houses, or they can be mounted on sidewalls outside of the houses, depending on the deployments and depending on the coverage that you may get inside the buildings. Okay. So we need to talk about, we want to talk about millimeter wave frequency bands. There are challenges and there are pros or advantages to use millimeter wave frequency bands. So I'll start with the pros of those millimeter wave bands. First of all, there are large chunks of spectrum, especially unlicensed spectrum, that can be used in those bands. And what this means is that you can deliver very high throughput through those bands. Okay, so that's a very big advantage for those frequency bands. Then we have massive MIMO, okay, so which is about beamforming and spatial multiplexing. And you can see that the size of the antennas is related to the frequency that is being used. So you can see a phased array over here with 128 elements at 3.5 gigahertz. You may see like 64 boxes here, like each box is a dual polarized antenna element, so cross polar antenna, I should say. So plus 45 degree polarization and minus 45 degree polarization. So you actually have 64 antenna elements with a plus 45 polarization, and then 64 antenna elements with a minus 45 polarization. And then you can see on the right side here an antenna with 512 elements, so 4 times 128 here at 28 gigahertz. You can see here that the size is significantly smaller, which is a great advantage for millimeter wave bands. So you can have more antenna elements and deliver through that. Finally, I will go through one of the disadvantages before I go through one of the advantages, the last advantage over here. Millimeter wave bands, one of the disadvantages is that the signal dies pretty quickly. Okay, so when you go to higher bands like 3.5 gigahertz, you will see that the cell range decreases already. But when you go to much higher bands like 15 or 28, 39 or 60 gigahertz, you will see that the cell range decreases pretty significantly. Along with that, you have signal variability, so much more variability, and this is partially linked to the fact that you have more gas and rain attenuation. For sub 6 gigahertz bands, so like 800, 1900 or 3.5, the impact of gas and for the gas and the rain is pretty much negligible. When you go to higher frequencies, so 20 gigahertz as an example, then you need to consider this. For some countries, the impact of gas and rain is actually very significant, and it makes it a bit less attractive for critical communications as an example. Something we learned as well through the trials at 28 gigahertz especially is that the impact of vegetation is very significant. Okay, so we'll go through that in a few minutes, but this is important to note. You cannot ignore the impact of vegetation for millimeter wave bands. So one thing that is good about the fact that the signal dies pretty quickly at 20 gigahertz on millimeter wave bands is that it is then very appropriate to use those bands for small cells. Okay, so this is where you can have an interaction between the LTE and the and NR technologies. You can add NR small cells within the LTE coverage, and then you have the ability to have dual connectivity between LTE NR and LTE and NR, which means you're pretty much aggregating the data from the LTE cells and the NR cells. So in a sense, you're adding NR cells to add capacity within the LTE coverage area. Now, in terms of propagation modeling in millimeter wave bands, so there are some key considerations. First of all, you need to start with accurate geodata. It was the case before for LTE, but it's now even more important to have building representation and vegetation. So for millimeter wave bands, We have seen that at 28 gigahertz, we've seen like a through loss around like 1 dB per meter typically, but we've also seen cases where the losses were 3 to 4 dB per meter at 20 gigahertz. So 3 to 4 dBs per meter, as you can imagine, this is a massive amount of loss that you see through the trees. So if you're more familiar with feet, that would be like about 10 dBs per meter that you will lose, 10 dBs per foot, sorry, that you will lose through the trees at 28 gigahertz. Okay, the gas and rain attenuation needs to be accounted for as well. And so this is important to note when you run propagation studies for millimeter wave bands. So this is a visual representation in 3D of 3D geodata that we can offer at Infovista, and that is very important to consider when you do planning for millimeter wave bands. So this is the new generation mapping data for 5G and automated planning. First of all, what you can see here is that within a group of trees, you may have different heights. Okay, so it's quite important to identify that and to make sure that this is captured in the geodata that you use for your network planning. You have high-resolution building footprints, and along with that, the building roof structure that is highlighted in this little square over here. And most importantly is the fact that you have the footprints for the trees that are well represented, as you can see in this particular picture over here. Okay, on this slide, you can see that the main message over here is that fixed wireless access at 28 gigahertz is a viable solution. Okay, so throughout the network planning, throughout the trials that where we've been involved, early deployments, we have seen that it works. Okay, this is very important to note. Some people did not think that it would really work, but it actually works very well. The coverage is actually a bit better than expected. We've seen like cell ranges around 200-300 meters. So that makes it pretty interesting here to deploy like radio sites as opposed to using using cable. And of course, this is important to understand. And you can see the impact of the trees that you can see over here with the red areas that are not super well covered because the trees are accounted for, and the trees are taller than the buildings over here, the houses. So it's important to understand. One last thing that we've learned through the trials as well and through measurements, okay, so drive tests, so, is that the accuracy levels of propagation modeling for millimeter wave bands is very much on par with the accuracy levels that you can reach with for sub-6 gigahertz bands, like the PCS bands at 1900 megahertz or 900 megahertz. So typical standard deviations around like 6 to 8 dB, depending on the geodata solution that you use, depending on the size of the cells, the environments, etc., etc. But this is very much on par with what we saw or what we've seen with for sub-6 gigahertz technology. So we'll now go through some presentation about this within Planet. So first of all, we'll talk about millimeter wave bands. So millimeter wave propagation modeling. You can see here like a small transmitter over here, like, and what I want to show you is that this is the picture with and without the trees. Okay, so this is in Atlanta. So without the trees, so you can see the buildings here, and if I add the trees now, you can clearly see that the trees will have a nice impact or a significant impact on propagation modeling. If I show you like a drive test here, okay, so this is a small drive test, and if I put some thematic map, you will see the information here. You will see the cell range, and then I can overlay this. I can overlay propagation on top of that. So this is one of the drive tests that we have. and I can show you the propagation on top of that. So if I go into the raster color, I will remove the interpolation so that we're looking at the same thing here. But you can see a very nice correlation between the propagation and the drive test measurements, which again means that you can have a very accurate propagation modeling for millimeter wave bands. Now, if we go into fixed wireless access planning, this is an example over here in Denver. Okay, so in the US of America, and you can see like a set of sites that were deployed or planned at 28 gigahertz. I can zoom in a little bit more here. So you can see the density here. So 28 gigahertz fixed wireless access sites. And then I can display fixed wireless access homes. Okay, so you can see here that we created CPEs, or we added CPEs to the houses in this particular area. Some of the CPEs are on top of the building. Some of them are within the buildings. Some of them on the sides, on the side of the houses. And then when we generate the predictions and the analysis for these sites, then we account, of course, for the exact location and height of those subscribers. So the result of these analyses can be seen here in the tabular editor or report preview or dialog that we offer in Planet. You can also export the information in Excel if you wish. But in this particular example, so you can see that we looked at about 10,000 CPEs, and then for each CPE, then you can see some information. So the serving cell to start with, the RSRP level at which it was served, second RSRP, second best server RSRP, you name it. So PDSC, HSANR, data rates, etc., etc. So then you can assess like which houses are covered and which houses will have a good data rate and which houses may not be served very well. Okay, let's now move on to our third topic over here, which is about massive MIMO. Okay, massive MIMO, a very key topic for 5G, and we'll start by describing the concept here. Basically, massive MIMO is about beamforming and multi-user MIMO and single-user MIMO. On this picture over here, you can see 3D beamforming, so elevation beamforming here with subscribers at different heights on the building here, and then subscribers that are spatially decorrelated as well on the horizontal plane or the azimuth plane here that you can see here. Okay, so it's about creating beams towards those users. MIMO can be used for various use cases. So 5G fixed wireless access is an example, as we just discussed, and then for 5G NR, it would be a key topic as well to maximize coverage and capacity. So there are three main questions that you may ask yourselves when you do massive MIMO planning. So first of all, what gains I may achieve? Okay, that's of course a very important concept. Like if I put massive MIMO antennas, how much more coverage am I going to get, and how much more capacity will I be able to offer in my network? The second thing is to identify where you should be deploying massive MIMO antennas. Okay, this is important. Those massive MIMO antennas are not cheap. Okay, they're more expensive than regular antennas, and this is because they improve coverage and capacity significantly in some cases. But in some cases, it may not be worth deploying those antennas. So identifying the sites for which you should be putting massive MIMO antennas is a key topic. Finally, you need to understand the impact of the traffic distribution on the gains. Okay, so the question is, like, what is the impact on that traffic distribution? Is it significant or not? And based on the trials where we've been involved, the answer is yes. So if all the subscribers are given at the same location, you may not get like very high gains, whereas if all the subscribers are at different locations, then of course you will get much higher gains because you'll be able to direct separate beams to those users, and you'll be able to use multi-user MIMO to reuse the same resource blocks and maximize the capacity. Okay, so what is massive MIMO? So I mentioned this a little bit in the introduction in the previous slide, but this is about two things, okay? Beamforming and multi-user MIMO and single-user MIMO, okay? On the left side here, there are two flavors of beamforming. So first of all, I start with the bottom one with true beamforming, as we call it, which is about directing the beams right towards the subscribers. This is done by applying a set of complex weights onto the antenna elements that compose the antenna. So complex weights, so amplitude and phase, and this allows you to direct the beams towards the subscribers. Okay, and now you have another flavor of this, which is beam switching, which is slightly different. Beam switching is also known as beam steering, or sometimes we also hear the concept of grid of beams, but this is referred to as beam switching over here. In this case, you have a set of predefined beams in different directions on both the elevation and azimuth angles. And the concept is to pick one of those beams that is the closest towards the subscriber, so you maximize the coverage, or SANR, that this subscriber will observe. So you may have a slightly different gain whether you use beamforming or beam switching. Now, on the other side of the line here, we explain the difference between single-user MIMO and multi-user MIMO. Single-user MIMO has been used in LTE networks for a long time now, and this is about sending multiple streams of data to the same users. So in this case, you double theoretically speaking, you can double the data rate for the user, so 2 times x megabits per second. In reality, you don't get 2 times, but this is the maximum limit here, theoretical limit. And on the multi-user MIMO side, on the other hand, you try to reuse the same resources for different users. So in this case, this could be done through more than 2 users potentially, okay? And this, instead of maximizing or doubling the data rate for a single user, you will have x megabits per second for one user, same thing for the other one, and you try to maximize the cell capacity here. From what we've seen with multi-user MIMO and beamforming, you can achieve gains that are 3 times to, or you can multiply your cell capacity, but between 3 to 8 times, depending on the traffic distribution. The traffic distribution has a very strong impact on the gains that you may see, and this is very important to understand. So this is why it's important to have accurate traffic maps in the first place when you do massive MIMO planning. So those traffic maps can be built from call trace data, they can be built from performance management data. You can use social media as well to help refining the locations of the users, but it's really key basically to understand where the traffic is. Okay, this is an example of coverage and capacity gains using massive MIMO antennas that we ran through using Monte Carlo simulations. So you can see that the distribution of the sector throughput is moved towards the right side. So a shift of the distribution, meaning that you're gaining capacity basically by adding massive MIMO antennas. And it's very important when doing the simulations to account for the traffic in 3D because as we just discussed, depending on where the users are on the elevation and the horizontal side, then the gains might be different. And we'll see this in a few minutes, but it's important to also identify where a massive MIMO should be input on which cell should be selected. So I'll go through that in the tool now. I have an example of a network over here in Tokyo over here, and I will zoom into a massive MIMO antenna over here. So if I zoom in, okay, so you can see this little small cell over here targeting this building here. So that building is a pretty tall building, like I think 100 meters, 100 meters if I'm not mistaken. So you can click here, yeah, around that. So 126 meters above ground level, 127. And the goal is to serve this building, because this building covers handles a lot of traffic. So if we look at this particular site over here, we can look at the massive MIMO antenna that was defined. So in this case here, we can look into this configuration. So this is an antenna that was defined with 128 elements. So 64 antenna elements with a plus 45 polarization, and then 64 antenna elements with a minus 45 polarization. You can see the service beams the service beams that have been defined over here, so in the different directions. So I can show you a couple of beams. So first of all, minus 15 and vertical angle of 0 degree. This one, let's look at this one. So you can see that it is slightly up tilted, and the goal here is to go and reach out to the subscribers that are in higher floors over here, which is particularly important, and one of the reasons why massive MIMO is important. So if you view that in 3D, okay, so I can rotate it a little bit. You should be able to see that. Okay, so you can see the nice up tilt there, and an ability to maximize the signal strength that will go towards the upper floors in there. Okay, so you can have like up tilts, down tilts, and this is all modeled in the antenna files that we offer inside Planet for beamforming and beam switching there. If I close this antenna now, I've generated a couple of analyses there so that we can look at the difference between using MIMO or not using massive MIMO or not using massive MIMO. The way this works in Planet is that you can decide at the link level which antenna algorithm will be used. So if you select automatic MIMO switching or diversity of MIMO, that means no beamforming. And if you select one of the last four here, it means beamforming is being used as well. Okay, so you can run simulations with and without beamforming. That's the main concept, and then it allows you to identify the gains that you may have. So I'll select a set of polygons over here, okay, around that site, and then I'll start with no beamforming, so we can look at the NR SSRSRP here in 3D. Okay, so you can now see it in the 3D viewer. Extend this a little, use the surface mode, and now you can see the coverage that you may expect in terms of our SSRSRP. I'll show you the color profile over here for SSRSRP. So this is what you get there. So you can see that for the bottom floors here, you have a nice high coverage or high signal strength for SSRSRP, but as you go higher up, you can see that the signal decreases. Okay, and that's typical. Typically, what you'd see with non-massive MIMO antennas. Now, with massive MIMO antennas, I can show you what you get now for the same view here with a massive MIMO antenna, and you can now see that this building is fully covered in purple, meaning that the beams were able to reach out the subscribers at the various heights here. And of course, that makes a huge difference when it comes to the SINR levels and SSRSRP levels that are seen within the building here. And so that means more coverage, more capacity that can be offered for those buildings. I also ran a couple of simulations on a set of cells with and without beamforming. And what you can do is select those simulations, compare them in terms of throughput. First of all, you can compare them on a global basis. On a global basis, what you will see, okay, is the difference. So this is the overall capacity that can be offered for with beamforming antennas. This is without, and then you can see the difference over here. So 90 megabits per second on top of 280, so it's around 30%, 35% over here increase in terms of capacity for this particular scenario. If I used a different traffic distribution, maybe I would get a different type of gains here. And now the second use case that is very important is to know which cells should be prioritized, in which case you go into the sector carrier tab over here. You can select the sectors here, the difference in terms of downlink throughput, and that gives you the cells for which there is the highest gains when you've shifted from non-massive MIMO antennas to massive MIMO antennas, or from non-beamforming to beamforming. So I can display, say, the top 20 cells or top 20 cells over here for which you see the gains in here. So obviously site cell 7.3, if I put 10 only, it will be easier. So cell 7.3, site cell 1.1, etc., etc. So you see that for those cells, it would make a lot of sense to put massive MIMO antennas. For other cells, it might be less interesting. And with that, I would like to go into a few conclusion sites here. So the advantages of Planet, and I think we've shown that through this presentation, it's the 5G NR readiness. We have a product today that can help you build 5G NR networks. We have full 3D network analysis that can be done, so you can generate your analysis and Monte Carlo simulations in 3D. And we have integration also with live data, so have an ability to import call traces. We can also leverage drive test within the application, and that can be helpful in the network life cycle. With that being said, I will open the mic now for a few questions that we may have received throughout the audience, throughout the presentation. Sorry.
All right, so thank you, Greg. We are now going to begin answering some of the questions submitted, but due to the number of questions and to keep to the allotted time, we will not be able to address all the questions that we received. So what we will do is we will get back to everyone who posed a question in very short time frame. But as a reminder, I would also like to tell everyone that you can still submit questions through the questions pane in your attendee control panel. So Greg, the first question is, why is massive MIMO so challenging to plan?
Okay, yep, that's a very good questions. I think there are multiple things to consider here, like multiple answers. The first thing to understand is, as you may have noticed in the presentation, is that the modeling of the antennas themselves is not that simple. Okay, so it makes it very important for the planning tools to offer like an antenna format that can handle those antennas in a simple and efficient manner. So it's very important to have a single file and have all the patterns within that antenna file. I think that's an important part. It's also important to have connections with the antenna vendors so that the antennas are well modeled and represent well what will happen in reality. Now, in terms of some of the other challenges is that you need to make sure that you understand your traffic distribution pretty well. The gains highly depend on where the users are. If the users are all at the same location, then the gains from massive MIMO are not as important as what you get if you have spatial distribution. So when you have high-rise buildings, that's a very good use case to use massive MIMO antennas, because you know that you have subscribers all across the building. So if you have beams that go towards those subscribers, then it makes a big difference. And the other challenging part is that you have to work in 3D. Okay, you need to work in 3D. The days are over where you could consider that your traffic was at ground level. As I just said, like if your users are in high rises, or you need to make sure that you account for the guys who are at the top floors or 50 meters above ground level, and the radio conditions there are not the same as what you have at the ground floor. So that's a long answer. I hope that answered the question. Thank you.
Thank you, Greg. Have another one here. What is the difference for massive MIMO planning between LTE Pro and 5G NR?
Okay, so we're getting into technical details here, but for LTE Advanced Pro, massive MIMO, so beamforming, is applied to the data channel, so PDSCH channel, while the control channels and signals, so the PDCCH, synchronization, RSRP, those channels are used like a broadcast pattern, so a fixed pattern. So there's no beamforming for those control channels and signals, and beamforming for PDSCH. On the 5G NR side, it's different. You can have beamforming for all the channels. So in some of the frequency bands, you may have beamforming for all the channels. For other frequency bands, you may only have beamforming for PDSCH. Depending on the equipment vendor as well, you may have different strategies. And you could have a different set of beams for synchronization signal and broadcast channel, as an example, with the concept of beam sweeping and different block IDs, and a different set of beams for the PDSCH channel, or CSI-RSRP as well. So again, so to sum things up on this one, so for LTE, only the PDSCH is beamformed, and for NR, you have more flexibility that needs to be handled for the planning of beamforming.
Okay, Greg. Thank you so much for today's presentation. And I would like to thank everyone for attending today's webinar as well. Once you leave the session, you will receive a short survey on the presentation, and we would really appreciate it if you would provide us with your feedback. You will also receive a follow-up email within 24 to 48 hours with a link to view a recording of today's webinar. So on behalf of